The purpose of the code is to take guessed inputs, take ambient conditions, and quantify the box, and use an iterative solution from formulas provided in order to converge upon the output temperatures. The first section would be the guessed inputs, and because the code performs correctly, these inputs are not particular upon what you enter at this point. As you can see, I entered 3000 Kelvin, which is unrealistic, but it still converges. The user input section is where you will take in information about your environment per testing day. So this is your ambient condition. I put at 293.1 Kelvin. This is your wind speed V, which is your velocity in meters per second. And then your I, which is in solar irradiance, which is also provided. The next section is your system inputs. This represents how your box functions. So basically in this here you consider that the air input is whatever the ambient temperature is. So in this case, if you were to tag boxes in line with each other, then your input temperature may not necessarily be your ambient temperature. These are the dimensions of the box. Consider the wetted perimeter, the internal cross-sectional area, which is necessary when you consider volumetric flow rate to find your internal velocity. Top surface area of the heater. This is needs to be considered if you are making the sides of the box painted, because that area there is dependent upon where your solar radiation is acting on the box. This is provided from the fan data sheet. These are both lookups based upon the materials that you're using. Another lookup. One of the assumptions we had made was that there was no conduction with the ground, and that was because we put an insulation foam beneath the air heater. The next section is retrieved inputs, and these are all dependent upon what operating conditions you have. So you can make a film temperature, which is dependent upon your ambient temperature and the internal temperature. Once you get a better estimation, you can look up better values for your conductance to your density of the air. These are all entered and calculated. The next section is the iteration solver here. So the logic here is that we enter into an infinite loop so that it can continuously look for a way to converge. The best way to do that is to use an infinite loop, and then the three values that we're looking for is your output temperature, your plate temperature, and your glass temperature. The way these equations work is that they're all dependent on each other, so we can't just use a system of equations and solve. We need to use iteration. So the best way of doing that is that we enter in those guessed values, and then as you enter into equations like this, or the ones above, we're able to come up with a more realistic answer each time until we check the percent difference of each one, and then once the percent difference is below 0.05%, then we give it a go ahead, and that's given for your output temperature, your plate temp, glass temp. And then upon receiving the check where x is equal to x plus 1, you will become x is equal to 3. At this point, it will break out of the loop and you are good to go, which means that all three conditions have converged onto an answer. Otherwise, it will exit the loop and we reset the value so that each criteria has the opportunity to go again. At the end of that loop, then we have a small vector here, which outputs our three needed temperatures. So if we are to run that, we will add the path. Then we are able to converge on these values where our 299 is our out, our plate is 320, and our glass temperature is 294. And as I said before, these unrealistic values of what we're guessing are not necessary at this point. However, if I was to change the wind speed to something quite chaotic as 10 meters per second, and we run it again, you would see these values might go down a little bit.